right, we're going to go through the review for the Unit 1 quiz. So question number 1 says, identify the key features for the graph shown. So the first one we have is the domain. To do the domain, remember domain is always going to be left to right. So for domain, you're always going to go from the left to the right. So if we look at this one, we got a nice parabola. It looks like it's just going to keep going. So I'm going to put little arrows on these ones and say we're going to go all the way to the left. Which way is my window going? So it would be that way to the left. It looks like we're going to negative infinity because we are just going to keep going left forever. Same deal if we go to the right, we're just going to go to positive infinity. And that's it. Since we're using the infinities, remember we always get the parentheses. That's the domain. The range, remember range, we always have to go bottom to top. So this one definitely has a bottom down here. The top, again, it looks like it's just headed all the way out to infinity. So I may as well just throw the top in there. But the bottom, we need to figure out what it is. So we need to read the graph. Now I have to be careful because down here it says 20. That means that these lines are all going to be 5. So 5, 10, 15, 20, 25. So we're starting at the bottom at negative 25. So again, we're going bottom to top, negative 25. Negatives down here for these. Negative 25 all the way to infinity. For the x-intercepts, that's where we cross the x-axis. That looks like we cross in 2 places this time. The 2 places we're crossing at. And again, we have to be really careful because this is 5, 10, 15, 20. Looks like the 2 x-intercepts are going to be at 5, 0 and negative 5, 0. So remember, these ones are coordinate points now. They are not both x's and both y's. Remember up here, these are both x's because it's domain. These are both y's because they're ranges, but these ones are coordinate pairs, and coordinate pairs are always x comma y, always with the parentheses. Same deal, the x-intercept, it's not always going to be the same as the range. So I'm going to use a different color just to show that it could be different. This time it's the same. It's just the bottom of the parabola. Again, it's not always the bottom of the parabola, but the reason it is because that's where we are crossing the y-axis. So this one's kind of nice that everything just kind of lines up. But if we move the parabola over, then our y-intercept is not going to be the bottom of the parabola or the top of the parabola. It'll just be a random point on the parabola that happens to cross the y-axis. Anyway, it's when x equals 0. So when x is 0, y is down here at negative 25. And again, this is also a coordinate point. For the next part, we have to find out where everything is positive. So for things that are positive, we want to go from the x-axis, and we want to be above the x-axis. So if we're above the x-axis, we're positive. So we're positive coming from negative infinity all the way until we get to here. Once we get to negative 5, then we stop being above the x-axis. We're just going up or down. Here we're up, which is positive. So negative infinity to negative 5. And then we're starting up again over here. Once we get back to 5, then we're back above. So we have to start again at 5 and then go out to infinity. Again, I'm using the parentheses because when you're at 0, you're neither positive nor negative. You are at 0 itself. So you don't want to use any square brackets in this case. But again, these are both x's because we're talking about the domain that it's positive over. So those are both x coordinates. So x is negative infinity all the way to x is negative 5, union with x is 5, all the way out to x is infinity. Negative is going to be kind of the opposite. It's going to be everywhere that we're below. 1, 2, 3, 4, 5, so I need new colors. So if I want to be below the green line, let's grab orange. So below would be for negative, and we can see it's this part of the parabola down here is all below the green line. It's all below the x-axis. So we're negative from negative 5 out to 5. And again, negative, these are x's. These are both x coordinates. Negative 5 is where we start being below the x-axis. 5 is where we stop being below the x-axis. For increasing, that's where we're going upwards. I need another new color. Run out of colors. Is that going to show up? There we go. So increasing, we're increasing on this half of the parabola. Because for every value that we're at, the next value is always going to be bigger in terms of y. So the y values keep getting bigger and bigger and bigger. And we said that was our definition for increasing. So we can see it starts down here at the y-axis. So we're going to start with 0, but it's just going to always keep increasing. So we're going to go from 0 to infinity. Again, when we talk about increasing, we're only talking about the x's. I want to know when in the x's is it increasing. I don't really care about the y coordinates. I want to know where in the x's are the y's going up, because that's what increasing means. Decreasing would be the opposite. Let's see if this pink shows up. Okay, so we're decreasing on the other half of the parabola, right? We keep going down on this side. So we keep going down from negative infinity all the way to 0. And again, those are x coordinates. Those are just x's. So there's a lot to answer for this one question. But again, this is like those homework questions that we did where there was just a bunch of parts that they throw it at you all at once. This is just identifying all the key parts to this one graph. So again, domain is left to right. Range is bottom to top. The x-intercepts, these are going to be where we cross the x-axis. The y-intercept is going to be where we cross the y-axis. Positive is where we're above the x-axis. Negative is where we are below the x-axis. Increasing, there we go, is when the average rate of change is positive between 2 points, or if the y's are going up. And then decreasing would be the opposite. This is if the y's are going down. So we get down here at the vertex, it's neither going up nor going down. It's not really, we don't know, because here it's going down and here it's going up. And that's why we've got the parentheses with the zeros. All right. Question 2 deals with the same graph. We have to find the average rate of change over the interval -5 to 0. So to do that, do I have any other good colors? Let's use this thing. So what I need to do is find -5 and 0 on the graph. There's -5 and there's 0. Remember, these are going to be x coordinates. This is like x2, and that's like x1 or x1, x2. You can flip them if you want. Since we did function notation, this is like a, and that could be like b. But we need these two coordinate points. So we know at 0, our function value is -25. That's f of b. Over here at -5, we're at the point -5, 0. So this 0 is like f of a. So we have our two coordinates. And again, you can do this with the slope formula if you want. But now that we have our two coordinates, we just kind of plug them into the average rate of change function. Remember, we're going to use this a lot with different types of curves. So it's a good idea to memorize the equation right now. That way you have it down for literally all the other test sets going to have it on it. But our average rate of change is f of b minus f of a over b minus a. And we just plop them in. So f of b is -25. F of a is 0. B is 0. A is -5. All right, we'll simplify. -25 minus 0 is -25. 0 minus -5 is regular 5. And we get an average rate of change of -5. Now we want to make sure it makes sense. So let's just double check. First of all, it's a negative. And that makes sense because it's in the section where it's decreasing. So we're going down as we go from the first point to the second point. So that makes sense. And yeah, I'd say if we were to draw that line, it looks like it kind of has a slope of -5. 1, 2, 3, 4, 5 down, 1 over. That makes a lot of sense. I guess we could have done that with rise over run as well if we wanted to. But remember, we're trying to find the slope between these 2 points. That's the same as the average rate of change. Again, that's a super long question, but when we did the homework for this section, we also saw that those questions were pretty long. All right, so let's get to something a little bit shorter, which is the equation for this equation, y equals absolute value of x plus 2. All right, so for this one, what is the equation for y equals absolute value of x plus 2 minus 5 reflected across the y-axis? So what we want to do is we want to make sure we're reflecting across the y-axis. So remember, y-axis is the one that goes up and down, so we want to flip left and right. But we also want to remember what the rules are for that. So if we're going to reflect across the y-axis, remember, x is going to become negative x. So that's what we have to do in this situation. So we have to turn the x's into negative x's. So that means instead of the equation y equals x plus 2 minus 5, we're going to get y equals absolute value of negative x plus 2 minus 5. Now that's not an answer choice. That doesn't look like any of the answers. So let's see what we can do to algebraically rewrite this. So what we can do is say, well, negative x plus 2, same thing as 2 minus x. And it looks like we got an answer. I'm thinking A. I'm thinking A might be the right choice. But let's just double check. We may as well graph it because we have the option to. So right here, I've already graphed the original. So absolute value of x plus 2 minus 5. So if I want to try the other one, let's just see. Let's visually check. Y equals absolute value of 2 minus x. Okay, that's looking good because it's on the other side of the y-axis. Minus 5. Yeah, that looks pretty good. That looks like we flipped it across the y-axis. I'm happy with my answer choice. I've checked my answer. I'm moving on. Already done with that one. All right. Next one, we've got which phrases are going to describe the transforms for f of x squared that give g of x equals x minus 1 squared minus 4. Okay, so we did some practice with these ones a lot in class. We just have to identify what the transforms are. So over here, remember, we've got the minus 4 outside the parentheses. Because it's outside the parentheses, we know this is going to be a vertical shift. Outside the parentheses, we follow the rules. Negative sign means we're going to go down 4. So let's just go ahead and quickly get rid of these ones and say up 4. Over here, x minus 1 squared. So when we're inside, we know it's a horizontal shift. We know we want to do the opposite. Since a minus sign, that means we want to go to the right. So we're going to go to the right one. So I'm pretty happy with D. Again, good one just to double check. We can bring up Desmos again and throw it into our graphing calculator. We're starting with the original graph is x squared. And you can type the f of x equals if you want. The new graph is x squared, x plus 1. And it's 1 squared plus 4. Double check I got everything right. X minus 1 squared minus 4, not plus 4. All right, so there we go. X minus 1 squared plus 4. And what we're going to do is follow any key points. Now, on the red graph, there's really only one key point, just the vertex. So what we want to do is just follow the vertex as we go from 0, 0 to 1, negative 4. So we went to the right 1, and then we went down 4. So that's it. This one's done. Again, easy to double check. Should be easy points. Next one, write using phrases all the transforms of f of x equals the absolute value of x that combine to result to the graph of g of x, or function g shown. So we know that f of x is the absolute value of x. And again, you can graph this in Desmos if you want to, see what absolute value of x looks like. I know that's what absolute value of x looks like, so I'm going to go ahead and just draw that in. And kind of just like the last one, what we want to do is we want to follow. So we want to follow the direction of the vertex because the vertex is the key point. So it looks like we're going that way, and then we're going up. Let me change the colors of these because I'll write them as separate phrases. Oops. So for the first one, let's make that one red. And so first one, we can see that we're going to the right. So we're going to the right 2. That would be a phrase. If you wanted to be very specific, you can say a horizontal transform or a horizontal translation of to right. Now in the other direction, let's change that one to blue. We can see that we're going up 1. So you can have this as your final answer if you want. But it's nice to be specific, so we could also call that a vertical translation. Of 1 up. All right, so that's what we got. Next it says write the equation of g of x. Well, we know what it does. We know it goes to the right 2. We know it goes up 1. So we've got 2 options. So the first thing we could do is we could just write, since we know g of x is a transform of f of x, if we really like our function notation, we could say that it's f of x. And we're going 2 to the right. So we're going to go right 2. And we're going 1 up. So we can go up 1. So again, we can just use the function notation if we want. That takes care of pretty much any graph that you've got or any function that you've got. If you specifically want to use the square root of x, well, then we would say instead of f of x minus 2, we would say the absolute value of x minus 2 plus 1. So again, both of these are correct. This one does the function notation, and this one does the equation. Technically, the function notation is also an equation, so that's why both of them are fine. Take your pick, but that one's already done too. We can see we're going really fast with these other ones. All right, next up, this graph represents f, graph 1/2 times f of x plus 2. So again, the idea is to identify all of the shifts and stretches and compressions. Here we've got plus 2. Plus 2 means we have to go to the left 2. And then out front, we got the 1/2. So 1/2 is going to be either a stretch or compression. Since it's less than 1, this is going to be a compression vertically by a factor of 2. Again, you can shorthand that and just say we're going to divide by 2, but we'll see it with the graph. It might be a little bit nicer. We want to identify the key points. So let's start off by identifying the key points. It's probably going to be all the bends in the graph and the endpoints. So I think that those are going to be my 4 key points. Now, if I wanted to, I could write those as coordinate points. But since we just have to graph this, I think I'm going to do it like geometry and say, all right, well, the first thing I want to do is go left 2. We always want to work from the inside out. So since the plus 2 is closest to the x, I'm going to pick that one to do first. So I'm just going to move all these points left 2. All right, well, I moved the entire graph left 2. All right, so that's done. So I did the red part. I did the left 2. Now I need to do the compression vertically by a factor of 2. Again, that's the same thing as saying we're going to divide all of our y coordinates by 2. So from 0 to 2, half of that is 1. From 0 to 1, half that is a half. From 0 to -1, half that's negative a half. And 0 to 0, half of 0 is 0. We'll draw our line. Let's make our line green. Can I get a regular line? I want a green regular line. So we'll draw a line, and draw a line. Maybe not perfect, but that looks pretty good. That's it. We're done. We don't have to do anything else. We did the first transform, we did the second transform. We're all set. If you do want to follow them as coordinates, let's just take this one as an example. It's at -2, 2. Again, you'd want to do the left 2 first. So -2, 2. If we go left 2, we only change the x value. So we'd want to do -2 on the x. And then we'd have to do the compression by a factor of 2. So we'd have to take half of the x, half of the y value, vertical compression. And that would be -4, 1. And then I could just plot that point, which I have in the same spot, -4, 1. So again, you can follow each of the coordinates. In this case, it's a little faster to do it like geometry class and just move the points. But you can also do it the other way. Number 7, graph the function f is shown. Domain is 0 to 50. What's the range of g of x equals 2 times f of x? All right, well, right now let's find out f of x because it wants the range. So the range of f of x is going to be, again, we're going to do low to high. So the lowest it gets is 0 down in these two spots. That's the lowest it gets. And the highest it gets is up at the top. That's the peak. All right, we got to read this graph. So 1.5 and 2, halfway between 1.5 and 2 is 1.75. And again, it hits both of those locations. We can see that the graph stops. It doesn't keep going. That's how we know we don't have a negative infinity over here. There's not the rest of the graph coming down here. It does stop in both directions. But that's f of x. We need to get g of x, which is 2 times f of x. So again, let's do the vertical stretch. By a factor of 2, because it's outside of the f of x. So if it's outside, remember it deals with the y's. So that means we're going to do the y's times 2. So these are both y coordinates. So what I need to do is multiply each of those numbers by 2. Well, 0 times 2 is still 0. 1.75 times 2 is 3.5. So the range of g of x is going to be from 0 to 3.5. And that's it. So that's what our range is for g of x. We're going to take this graph and just stretch it out so that's twice as tall. There we go. Number 8, function f of x is absolute value of x is graphed over the interval -6 to 3. Which translation of the graph has the domain -9 to 0? So again, here we want to see we got domain, and we have to remember domain is the x's. Domain is going to be the x values. So of my transforms, this is a y value, and that's a y value, so I'm going to get rid of those two right away. I know those are y values because they're outside the absolute value. So I have to recognize, okay, so I'm going to go from f of x is -6 to 3. G of x, my new function, is going to go from -9 to 0. So you're going to have to identify what's going on here. Now, this is where things get tricky. We don't want to do this mathematically. We want to think about this in terms of what does this look like on a graph. So on a graph, -6 to 3 means I'm going to go from here to here. G of x goes from -9 to 0. So what we're doing is we're taking f of x and we're going to shift it to the left. So I have to pick the one that says I'm going to the left. So again, from the black bar, I go to the left. I'm going left 3. So the one that actually represents left 3 is going to be x plus 3. Again, that one might not be as intuitive, and you might say, well, I have to subtract 3. But remember, if I'm subtracting 3, if I'm going to the left 3, that's a plus sign inside the equation. So we got to be really careful with this one. That one can trip some people up. Now, even though we could graph this one in Desmos, it's probably not a great idea. Since, again, we're switching out all of our things. We're switching out our interval. We don't really know exactly what we want for our result. So I probably would not put this one in Desmos, even though we could. I would probably just leave it like this and leave it as is. For number 9, what's the rule that defines the graphed function? Looks like I'm in the way of this one. We're going to put some solid dots here. They are solid, even though they're not really marked as solid. They are solid. So we need to come up with the function rule. So that means that we need to get an f of x that works for both parts. So we're going to get a top equation, a bottom equation. I want 2 equations because there's 2 lines. So the first one, though, at least I can tell what I'm going from. So 1, 2, 3, out to 1. So for the first equation, I know I'm going from -3 to 1. So we'll write -3 x to 1. Closed dot, little line underneath the less than sign. Open dot, no little equal sign. Again, kind of like Algebra 1 where we did the graphing with the inequalities. Then I have to do the second one. On the second piece, we're starting at 1, 2. And we're going out to 1, 2, 3, 4. So down here, this would be x equals 4. So for the second piece, we know we're going from 2 to 4. Since they're both solid dots, they both get the little equal sign. So there's no rule that says only one gets a solid line, one doesn't. There's no rule that says it has to be on one side or the other. You have to look at the graph. There's no rule for left or right or anything like that. You need to look at the graph and just decide which dots are open and which dots are closed. Now I still have to get the equations. Well, we can do that with the black one, which is the first one I'm doing. I'm going to do that one in black. So right here we can see we've got the y-intercept. So we know that the y-intercept is -1. Pretty good. We can get the slope by counting. We can do rise over run. We may as well just do the average rate of change over the whole thing. 1, 2, 3, 4, up 4. 1, 2, 3, 4, over 4. So we're going to rise 4, run 4 that way. So our slope is 4 over 4, or 1. So in our equation in y equals mx plus b form is 1x plus 1. You don't have to write it as 1x. You could just write x. But I'll put the 1 there just so we can see where these are all coming from. Oh, not plus 1. I think I caught myself. -1. We're at -1 down here. Just because those look like absolute value bars, I'll put the little fancy ones. So we know that's what the first equation is. It's the graph of 1x minus 1 over the domain -3 to 1. So the other one, we got to do the other line now. This one's a little bit trickier because we don't have a y-intercept. So we got a couple options. We can either extend it out to get to the y-intercept, or we can go ahead and use the average rate of change formula to get the slope. I'm thinking that's probably going to be the better idea because we can read these points pretty easily. 1, 2, 1, 2, 3. 4, 1, 2, 3. So if I do the average rate of change or the slope formula, so we can do x1, y1, x2, y2. I guess I'll do slope because we're just finding a slope. -3 minus 3, so y2 minus y1. Actually write the whole formula down. Over x2 minus x1, so y2 is -3 minus 3 over 4 minus 2, so -6 over 2. So we know that the slope is -3. Again, negative makes sense. And if we want to check down 3 over 1, yep, down 3 over 1, yep, okay. So we have the slope, so we know it's -3. Again, I don't have the y-intercept, so I think it's going to be easier to use point slope form, x minus x1, y minus y1 equals mx minus x1. I'm thinking that's going to be a little bit easier than anything else. So if we plug them in, we get y minus 3 equals -3x minus 2. Distributing this -3, y minus 3 equals -3x plus 6. Add 3 to both sides, and we end up with y equals -3x plus 9. Okay, so we have our thing over here, -3x plus 9. And then we're all set. We're actually done. Now, again, this kind of requires you to have remembered our friend point slope form back from Algebra 1 and geometry class, because we used it in both of those classes. If you forgot, there is a way to do it without having to count. All the way back to the y-intercept, we remember that this is a line. So for our line, what we want to do is we want to take our start and say, well, we're at 2, 3 here. So I need to apply all the transforms. I'm going to start with y equals x. And I can see I need to go over 2. I need to go to the right 2. So if I'm going to the right 2, this is kind of interesting. That means that now we got y equals x minus 2. All right. Well, next thing I see I got to do is I got to go, this is, of course, from the origin. From the origin, I also need to go up 3 now. Well, if I need to go up 3, y equals x minus 2 plus 3. Oh, we can do this with transforms. Look at that. And we already know the slope, because remember, the slope is the same thing as a stretch. So if we have a bigger slope, we're stretching out our line. So I know that we have a vertical stretch of -3. And I also know, well, that's not to put a plus sign there to confuse people, but I also know that it's upside down. So let's do vert stretch of regular 3. And we flipped. So instead of going up, we're going down. It's hard to do backwards camera. But our line's going down. It's not going up like the first one was. So we also know we have a reflection over y. So that means that I want a negative sign with a 3 and x minus 2 plus 3. And look, we actually are going to get the exact same thing if we distribute. Y equals negative 3x plus 6 plus 3. Y equals negative 3x plus 9. That's really cool. And again, that's where one of the ways that you can develop point slope form. In Algebra 1, we did it with the slope formula. We kind of divided to get this, or I should say multiplied. But you can also develop point slope form just by saying, hey, wait, it's just all the transforms. Very interesting. Again, it doesn't really matter which way you do it. This is our final answer. So just a little bit of a bonus thing in case you forgot. Our friend y minus y1 equals mx minus x1. Anyway, last question. Table shows admission prices the Superbike race at the Painesville Race Circuit. So here we've got age in years and then the admission price. So if we're under 4, we are free. So let's see. It looks like each line is 5. So we'll have to estimate, not when we are 4, but we have to be under 4. So we want to have an open circle. Because if we're 4, we're not under 4. It's free, so you pay $0. Done. If we're 4 to 17 years old, so we want to go just straight up from our open circle, but we have to pay $20. So we know we have to pay $20 if we're 4 years old. Hopefully our parents are paying. And then 17, so 10, 12.5, 15, 17.5. 17, well, when you're 17, you still have to pay that, so you got to do another closed circle. Now here's the interesting thing. Next one starts at 18. You got to pay full price. You got to pay $35. So we can come up to 35. That's not the issue. But 18 is more than 17 and a half. 18 is over here. So you're going to have to decide what you need to do if you're 17 and a half years old in this case. If you're 17 and a half, you're technically not on the chart because it's only 4 to 17. And then it's 18 to 62. So technically you don't exist. If you are 17 and a half, you can try and get in free. They'll probably say that's close enough to 17, and they'll probably extend you a little bit out to 18. But technically, by this table, that's not true. You don't have to pay because you're not on the chart. There is no price for you. But anyway, this goes until you're 62. Let me move myself out of the way so we can get to 62. This is 62 and a half, so 62 should be about right there. Again, just like if you're 17 and 17 and a half, that works. And then 63 and over. So 63 does count now because it is 63 and over. So everybody who's above 63 also counts in this section. This is the senior discount, so you get a little discount. 63 is right there, and then over would be out to infinity. So even if you were infinity years old, you'd still have to pay $30. All right. So that's what our graph looks like. It's a piecewise function. We can see, again, with most piecewise functions, each line represents a different part of the story. The first is the black part is if you're under 4, that part of the story. The red and a little bit of blue, in case you want to put it there, is kind of if you're getting the child or the student discount. The purple line is when you're an adult and you pay full price. And then the green is for if you get a senior discount ticket. So kind of makes sense. The pieces match up with reality. So these piecewise functions are important for a lot of real world things. Next, it says identify the domain. Again, this is one that you're going to have to be very careful about. So if you want to include the little blue piece, which again, if you want to include that little blue piece, you should include a little bit over here too, where you're 62.5. If you want to include the blue piece, also under 4, technically would be that. Again, doesn't really make sense to be less than 0 years old, but I guess if you're not born yet, you still get in for free. Kind of weird to think about. But I'm going to put a blue dot down here. Where's blue? As like the intended response. 0 out to infinity. Is this logical? Does this make sense in the real world? No, not really, because you can't be infinity years old. So you might want to say like 0 to 200 years old. That's fine. That's a choice for the domain. The wackiest domain you can get would be, since it does say under 4, technically that would be negative infinity to 4. And we can go all the way till we're 17. So the wackiest domain says, no, when you're 17, you stop. And with your 17.5, you don't pay anything. It starts back up again once you get to 18. And then that goes until you're 62. And then when you're 62.5, well, you're not on the chart anymore, so you have to pay. So then it starts up again, goes to 63, and it goes out to infinity years old. So that's like the wackiest domain you could get. The intended response is probably the blue domain over here. Just say 0 to infinity, so that makes sense. Again, if we're thinking about this in terms of the real world, yeah, you're going to get people who are 0 years old, so babies, all the way out to people who are unknown years old. So the infinity is going to kind of represent an unknown. If you want to do it in set builder notation, this would be curly brace x, 4, and this is going to be 0. Well, just x is greater than 0, I guess. Greater than or equal to, because we've got the bar. I'm not going to put the infinity afterwards. We don't need to do a triple inequality here. Just x has to be greater than 0. For the next part, for number 12, identify the range. So the range is going to be also somewhat strange. So we don't really want to use the interval notation here. Because if we did, we would have to say it's free, unioned with $20, unioned with $35, unioned with $30, and that's a lot to write. So the interval notation, probably not the best in this case. The reason we have to write all these out separately is there's a whole bunch of gaps in here. Like, we can't get anything in between any of these prices. So for this one, it's probably best just to write it in the interval notation. So y, 4, and then you can just write the numbers 0, that's not a 0, 0, 20, 30, and 35. That's much cleaner than the interval notation. So I'd recommend the set builder notation for this one. This one kind of either or. Both of those are about the same. But I would definitely recommend the set builder notation for the second one. That's it. That's everything that's on the test. So you can see it's a pretty good review. Not review, but a pretty good test for just the first 3 sections that we did. So the first question pretty much covers all of 1-1, right? We had to do all those key features of the graph. Then we did 1-2, which was all of those different shifts and transforms. And then down here, we had those couple piecewise functions from 1-3 at the end. So it can be a pretty tough test if you're not careful. But as long as you kind of keep things a little bit more calm with like, okay, there's only things from 1-1, 1-2, and 1-3. And I know what the key points are, identifying key features, all the transforms, piecewise functions. It's those 3 topics are the main topics. If you keep that in mind, things should go pretty well for this one. All right, that'll be about it.